Next part, we are going to focus on the periodic properties. First, factors affecting trends in periodic table. A. Nuclear charge. Nuclear charge is dependent on the number of proton. As the proton number increases, the nuclear charge also increases. Thus, the attraction between the electron and the nucleus increases. B. Screening effect. Screening effect, also known as shielding effect, refers to the shielding of electron from the electrostatic attraction of the positively charged nucleus. Shielding effect increases with the number of electrons present in an atom. Hence, the effectiveness of the shielding effect of the electrons on the valence electron are given below. Number 1, electron in the inner shell provide effective or significant shielding effect on the valence electron. Number 2, electrons in the same shell exert a negligible shielding effect on one another. So these two things that you need to remember for shielding effect, or we can call screening effect. It's the same. Next, effective nuclear charge. What is effective nuclear charge? It's the indicative of the attraction. More specifically, the net attraction. The net attraction of the nucleus on the valence electron. This is because shielding effect is effective because there's this shielding effect of the negatively charged electron, preventing the higher orbital electron from experiencing the full nuclear charge by the repelling effect of the inner shell electron. When the increase in nuclear charge outweighs the increase in shielding effect, effective nuclear charge increases. Right, so we want to look at this thing called effective nuclear charge by considering the forces of these two factors, by considering the two factors, effective nuclear charge as well as shielding effect. Basically, effective nuclear charge is equal to nuclear charge minus the shielding effect. Right, next, distance. The distance between the outermost electron and the nucleus. So what you need to know most important is this: the number of principal quantum shell increases, the distance of the valence electron from the positively charged nucleus increases. So there will be weaker attraction between the valence electron and the nucleus. Next, inter-electronic repulsion. Alright, electron in the same orbital experience additional repulsion from one another. So you need less energy to remove it. You need less energy to remove the electron. 4.1, ionization energy. What is it you need to know here? For ionization energy, you need to know definition. It is defined as the energy required to remove 1 mole of outermost electron from 1 mole of gaseous atom to form 1 mole of singly charged gaseous ion. Alright, so this is the equation you need to write. And you can write down ionization energy is a positive value. This positive value can be coded from the data booklet. So and so forth. Alright, take note the state symbol is gas. Alright, and it starts from 1, 1, 1. 1m gives you 1m plus and 1 electron. So similarly, the definition for second IE, second IE starts from 1, 1 also gives you 1. It's also gas. How do you define that? It's also the energy required to remove 1 mole of the outermost electron from something different now, from singly charged gaseous ion to form also 1 mole of doubly charged gaseous ion. Alright, so the word gaseous is very important. We brought the word gaseous in both the cases. Alright, outermost electron, 1 mole. Alright, your definition will be wrong. Okay, so as we mentioned just now, IE are endothermic, positive value. So this is first IE, this second IE. So second IE also can be obtained from the data booklet. It's a positive value. So with all this knowledge in mind, we now need to do this. Explain the IE across the period as well as down the group. Alright, do take note, across the period we explain in terms of shielding and nuclear charge. down the group in terms of electronic shells and nuclear charge. So let's take a look here. First thing you must do to reproduce the graph. Alright, if you take a look, this is for period 2. You see a general increasing term, increasing trend. This is for period 3, there's an increasing trend across. But you realize that the blue curve is higher than the yellow one. Than the yellow line. Alright. Second thing, you realize that there's always anomaly. Down here, there's some decrease before it increase in general. So these are things we need to learn. So you need to draw and sketch the graph and explain. So how to explain? First part. Across the period, i.e. generally increases. Because nuclear charge increases. Alright, why does it increase? Because proton number increases. Successive electrons are added to the same principal quantum shell. So there is no change in the number of inertial electrons. The increase in shielding effect is negligible. Hence, effective nuclear charge increases because the increase in nuclear charge outweighs the increase in shielding effect. Therefore, the valence electrons are more strongly attracted to the nucleus and you need more energy to remove the valence electrons. Hence, IE increases. Right? Irregularity. Why so? Now, take a look. The electron to be removed from magnesium is from here. 3s2. Whereas the electron to remove from aluminum is from 3p1, which is slightly further away. The 3p orbital is further away. And it experiences additional shielding effect by the two 3s electrons. These two factors outweigh the increase. This factor outweigh the increase in nuclear charge from magnesium and aluminum, resulting in weaker attraction by the nucleus. Therefore, you need slightly less energy to remove the electron from the 3p orbital in aluminum than that in the 3s orbital in magnesium. This applies to boron and beryllium as well, because boron, the electronic configuration is 1s2, 2s2, where for beryllium is 1s2, this 2p1, and boron is 1s2, 2s2, 2p1, beryllium is 1s2, 2s2. So for boron, it will be lower because from the 2p1. Alright, next. For sulfur and phosphorus is different explanation. The electron to be removed comes from here, the 3p3, whereas from sulfur comes from here, this one, 3p4. Both are in the same orbital, but why so? Why is then sulfur lower? Because in sulfur, the paired electron in the 3p orbital experience inter-electronic repulsion. This factor outweighs the increase in nuclear charge from p to s, resulting in weaker attraction by the nucleus. So you need less energy to remove the paired 3p electron. This is the same for oxygen and nitrogen. Nitrogen is 1s2, 2s2, 2p3, whereas oxygen is 1s2, 2s2, 2p4. Similar configuration. So when answering this question, you need to stick and draw. Draw the electronic configuration. Right, so please remember that. Next, for down the group, you have to explain based on the distance factor. Down the group, IE decreases because the nuclear charge increases with the number of protons increases down the group. But more importantly, the distance of the valence electron also increases because of the increase in number of filled quantum shells. This is the main reason. So do not talk about shielding effect, all these things, do not talk about it. Okay, and the valence electron are hence less strongly attracted to the nucleus. You need less energy to remove the valence electron, i.e. decreases. Right, so this is basically the trend of IE or across the period down the group and plus the anomaly. Alright, so in this case, they are of different period. In exercise 5, you compare different period as well as different group. Alright, one is noble gas. Alright, you can see, whereas one is group 1. So how then do you explain? The more important factor in this case, if you were to take a look, is based on distance, because the valence electron is in a higher quantum shell, higher principal quantum shell. Alright, so it will be less strongly attracted, okay, because it's further away and has less energy required to remove it. Now, the same explanation that you use for ionization energy can also be used for atomic radii. First thing, what is the definition of atomic radii? Atomic radius of an atom is the distance of the nucleus to that of the electron, the outermost electron, outermost shell of electron. And across the period, you realize that the atomic radii decreases because of the same reason that we discussed just now about nuclear charge increases, successive electron added to the same principal quantum shell, increase in shielding effect is negligible, alright, and hence effective nuclear charge increases, and hence the valence electron more strongly attracted, and thus your atomic radius decreases. Now the group also the same reason, the atomic radii decreases. Why? Because the nuclear charge increase, because the number of protons increases, but the distance of the valence electron becomes further due to an increase in number of principal quantum shell. Valence electron less strongly attracted, atomic radii decreases. So it's basically the same template, alright, as that of ionization energy. Please do the reading for the definition of van der Waals radius, covalent radius, and metallic radius. Alright, although it's self-read, but it's included in the syllabus. Let's focus a little bit more on ionic radius. Alright, ionic radius is the radius of the ion, spherical ion in an ionic compound. So let's take a look. To compare why ion have a smaller radius than that of the parent atom, that is because the number of protons remains the same. Hence, nuclear charge is the same for the cation ion. But who got less electron? The cation ion has less electron. And as well as one less shell, one shell less. Alright, because you take a look, the 3p shell down here, the principal quantum shell 3 is no longer there. This one is no longer. Okay, this is no longer there in the cation ion. Hence, the valence electron experience lower shielding effect and more strongly attracted to the nucleus, resulting in the shrinking of the electron cloud and hence smaller radius. But for the N-ion, it's slightly different. For the N-ion, the radius of the N-ion is larger than that of the parent because the proton, hence nuclear charge remains constant, alright, because there's no change in proton. But the electron is now more. The N-ion has more electrons. So there's an increase in repulsion between electron in the valence shell, resulting in the expansion of electron cloud. Hence, the radius will be bigger. Then what about across the period? Just now we are talking about the parent atom to the cation ion, parent atom to the N-ion. What is it then about across the period? Across the period, the ionic radii decreases. You will notice that down here, actually for the radius, it's two separate graphs. One for the N-ion, one for the cation ion. One for N-ion, one for the cation ion. Alright, this is for the cation ion, this is for the N-ion. For the next period, this is for the cation ion, this is for the N-ion. It's two different graphs, two different lines, unlike that of the atom. Why? Because it has two different shells. For the N-ion, it has one extra principal quantum shell. Alright, so please note that. So the nuclear charge increases because of increasing number of protons, but the cation ion or the N-ion are isoelectronic, hence the shielding effect is the same. Effective nuclear charge increases, valence electron are more strongly attracted, so the size of the electron cloud decreases, ionic radius decreases. But from Al3 plus to P3 minus we mentioned just now, alright, P3 minus has an extra shell of electron, hence you realize that the line is not continuous. The valence electron of the P are further away from the nucleus and less strongly attracted. And the ionic radius of P3 minus is much larger than that of Al3 plus. That's why it's two discrete lines. Alright, one is the cation ion. Right? And after that, there's another one for the anion. It's higher up. This graph is higher up, different. Okay, so do take note of that and make sure you draw it correctly. Next concept is electronegativity. Know the definition is the measure of the ability of the bond atom in a molecule to attract the shared pair of electron to itself. The explanation for electronegativity is exactly the same, alright, for that of across the period, alright, for ionization energy as well as atomic radius. So just take note that the electronegativity increases across the period. This is something very important. The rest of the part is the same. It's the same template. Okay? Except for last line, electronegativity increases. This part. Alright? Because your proton number increases but shielding effect remains the same, hence effective nuclear charge increases. For down the group is as well the same. Down the group, you need to know this. It decreases. Again, it's based on distance. Take note. Alright, so the whole template here is the same except for the last statement. Alright, so I'm going to go through this very fast, and last but not least, the last section, chapter 5. Alright, experimental determination of ionization energy. You must be able to sketch the graph like this. Sketch. What do you learn from here? You realize that there's a big jump between the first electron to be removed, and the second one. Alright, there's another big jump down here. And you count carefully over here, there are actually how many electrons? 8 electrons. What does all this tell you? It tells you this. First thing, how come as you remove electron, the IE increases? Because the number of electrons decreases, but the number of protons remains the same. Hence, stronger attraction between the nucleus and the remaining electron. You need more energy to remove the electron from an increasing positively charged ion. Right, that's why you see this graph, it generally increases. Alright, but how come there's a big jump between the first one and second one? What can you actually interpret? Alright, you actually interpret from here that the first electron is from the valence shell, the second one is from the inner shell. Hence, you need more energy to remove this electron because it's closer to the nucleus. So all this actually tells you that the large jump from the first IE to the second IE tells you that there's one valence electron, and hence this element is group 1. And because you don't know the total number of electrons, you cannot determine which element it is. You can only write down the valence electron configuration. This is NS1, where N represents the principal quantum number. Alright, you can try out this exercise. Alright, and you will realize that there's a big jump between here. 1, 2, 3, 4, 5, 6, 7. There's a big jump between 6 and 7. Big jump. So this element is likely to be in group 16. Alright? This element is likely to be in group 16. Okay, summary. Please go and look through the summary on your own. And this will be the end of the chapter. Alright? And also please also look at the history of the atomic structure and the model of atom. Alright?